The fundamental theorem of calculus is also written in one other form that's sometimes called the net change theorem. So the net change theorem says that for any continuous function, capital F of x, the difference of values of that function from two x values is just the integral of the derivative of f. So this is exactly the fundamental theorem of calculus, because the derivative of capital F we would usually write little f, and if you do that, this is exactly the fundamental theorem of calculus. But it sort of has a different spirit, because the fundamental theorem of calculus concentrates really on the function you started with, whereas the net change way of stating this really concentrates on the function capital F instead of little f. So this is called the net change theorem because on the left-hand side here, this is the change in value of capital F between two x values. And another name for the change in value of a function would be delta f. So it's a change. And so that's why this is called the net change theorem. Sort of the slogan version of this is to find a change, integrate a derivative. So with that in mind, let's look at some examples. So suppose that water flows into a tank at this rate, given by this function f of t, and that's in gallons per minute. How much water flows into the tank in the first 10 minutes, so from t equals 0 to t equals 10? Well, we want to know, so what are we trying to find? So how much water flows into the tank? This is a change in the volume of the water, right? So we want to know the change in the volume of water in the tank from t equals 0 to t equals 10. And by the net change theorem, this is the integral from 0 to 10 of the rate of change, or which is the derivative of the volume dt. But the rate of change of the volume, that's exactly the rate at which water is flowing into the tank. So this is really just f of t. So we can just integrate f of t, which is 2 cosine t plus 2 dt. All right, so take an antiderivative. So antiderivative of cosine is sine, so 2 sine of t plus, and then an antiderivative of 2 is 2t. And we need to evaluate this from 0 to 10. Pause for a moment to check that this antiderivative is correct. So derivative of 2 sine t is 2 cosine t, and derivative of 2t is 2. So this antiderivative is correct. Now we can just plug in our bounds. So 2 sine of 10 plus 2 times 10 is 20 minus 2 times sine of 0 is 0 plus 2 times 0. So this part is all 0. And so the amount of water that's flowed into the tank over those 10 minutes is 2 times sine of 10 plus 20. And if we wanted a decimal approximation for this, we could dump it into a calculator. One common example of a net change is a displacement, right? If an object is moving back and forth along a line, if you compare where it started to where it ends up, that's its change in position. And so a change in position by the net change theorem is the integral over whatever the times are that you're talking about, the integral of the rate of change of position. But the rate of change of position is just a velocity. So if we want to find the displacement of an object from t equals 0 to t equals 4, we can just integrate the velocity function. So displacement is change in position, and that's the integral from, for this example, the integral from 0 to 4 of 1/2 t minus 1 dt. So now find an antiderivative. So it's 1 over 4t squared minus t. And let's plug in our bounds. So 1 over 4 times 4 squared minus 4 minus, and then we have to plug in our bottom bound, 0 minus 0. So 4 minus 4, and that's 0. So the displacement of this object from where it started is 0. In other words, after 4 time units, it's back to where it started. Now, one thing you have to be careful about when you're talking about an object moving back and forth along a line is you have to make the distinction between the displacement of an object and the distance that it traveled. So this object, its displacement is 0, which means after 4 time units, it's back to where it started, but it is moving around in the intervening time. You can tell it's moving around in the intervening time because its velocity isn't 0 the whole time, so it is moving. So the displacement is 0, but let's ask what is the total distance that it traveled. So that's a different question, right? The reason that the displacement came out to be 0 was because sometimes the object was moving to the right and sometimes the object was moving to the left, and it moved an equal amount to the right and to the left. So if we want to find the total distance traveled, what we need to do is, instead of integrating the velocity, right? The velocity is sometimes positive and sometimes negative, but to get the total distance traveled, we want to treat all velocity as being positive so that none of it ever cancels out. In other words, we need to integrate the absolute value. So this is going to be the total distance traveled. And you can see that this is going to be different than the displacement because the integrand is a different function. It's an absolute value instead of just the velocity function itself. So this is the integral from 0 to 4 of the absolute value of 1/2 t minus 1 dt. So, all right. Now we're running into a bit of a problem because if you think about all of the derivative rules that you know, none of them produce an absolute value. So in other words, there's no nice integration rule for an absolute value. So we're kind of stuck here, the way it's written, because of the absolute value here. Well, what we can do is, the thing about absolute values is sometimes the absolute value just puts an extra minus sign on something, and sometimes the absolute value just leaves it alone if it was already positive. So what we need to do is figure out this stuff inside. Where is this greater than 0, and where is it less than 0? Because if the stuff inside the absolute value is bigger than 0, the absolute value leaves it alone. And if the stuff inside the absolute value is less than 0, then the absolute value puts an extra minus sign on it to make it positive. So let's look at 1/2 t minus 1. We're going from 0 to 4 here. And 1/2 t minus 1 looks something like this. Right? We want to know where is it switching from positive to negative. And if you set this equal to 0 and then solve for t, you get t equals 2. So what we need to do is split this integral up at t equals 2, because that's where this stuff inside the absolute value switches sign from negative to positive. Fortunately, we know that we can split intervals of integration up. That's one of the properties of integrals that we know. So we can rewrite this integral as the integral from 0 to 2 of the absolute value of 1/2 t minus 1 dt plus the integral from 2 to 4 of the absolute value of 1/2 t minus 1 dt. Okay, now for this first integral from 0 to 2, for these t values, the stuff inside the absolute value is negative, and so the absolute value just puts an extra minus sign on it. So the integrand for this first one is minus 1/2 t minus 1. Okay, plus, and now for this second integral from 2 to 4, for these t values, 1/2 t minus 1 is always positive, and so the absolute value just leaves it alone so that it stays positive for those t values. All right, so now these integrands are both things that we can handle in the usual way. if you ever need to integrate an absolute value, this is the usual way to do it. You need to figure out where the expression inside the absolute value is positive or negative, where it switches, split the integral up wherever it switches from positive to negative, and then integrate each piece. Okay, so now we can finish this one up. Let's move this minus sign outside the integral. Let's write down an antiderivative for 1/2 t minus 1. That's 1 over 4t squared minus t. And this is going to be from 0 to 2, plus, and then integrate again, 1 over 4t squared minus t, from 2 to 4. And now we just need to do all the arithmetic of plugging everything in. So, let's see, for the first one, this is going to be 1 over 4 times 2 squared is 4 minus 2 minus, and then we need to plug in our 0, but that's going to give us 0 for this one, plus, and let's see, so 1 over 4, we're plugging in our top bound here, 1 over 4 times 4 squared minus 4 minus, and then plug in 2, so 1 over 4 times 2 squared is 4 minus 2. Okay, so minus, let's see, we have this is 1, 1 minus 2 is minus 1, plus, and then over here, this part comes out to be 0, and this part comes out to be minus 1, but it has another minus sign, so it's plus 1. So altogether we get 2, it looks like. So this came out to be positive, even though the object ended up at the same place it started, because the object must have, as it was sliding back and forth, it must have started here, it slid this way for a while, and then it turned around and slid back. That must be what happened. So it slid 1 unit to the left, and then it slid 1 more unit back to the right. And so the displacement is 0, even though it traveled 2 units. So if you are working with an object sliding back and forth, be careful to distinguish displacement and distance traveled. Distance traveled is the integral of an absolute value of velocity.